stretching, folding, and then reinjection. This is in phase space. It's sort of like a main mechanism of chaos in continuous dynamical systems. This is showing that repeated stretching and folding on the Rossler attractor. So just different steps of, if you take an individual sheet, it goes around once, then it's two, those two go around and they also double. So you have this doubling of sheets that leads to, if you were to take a cross section, that Cantor set type structure. This is the schematic of the Rossler attractor, but in the Lorenz attractor, we have a very similar thing, and Lorenz called this an infinite complex of surfaces. The problem is, if you try to take a Poincare section on the Rossler attractor, that factor of shrinkage is probably on the order of thousands. So it's very hard to resolve numerically what this complex of surfaces looks like. And even if we were to do it for the Lorenz system, for the typical values of the Lorenz system, people were having trouble in the 70s when they had discovered this Lorenz system that was found by Lorenz 10 years earlier. They're having difficulties in resolving that infinite complex of surfaces, because after going around the attractor once, the volume in phase space is typically squashed by a factor of 14,000. So very difficult. So Michel Hénon was at a talk where someone was talking about this numerical difficulty of resolving what the shape of the attractor looks like, that infinite complex of surfaces. So he came up with a map that had similar properties, but then he could see the infinite complex of surfaces. So we're going to talk about what Hénon did. So this is the Hénon map, and he published this in a paper in 1976. You notice there's a lot going on in the 70s, because this is when people had rediscovered Lorenz and were really excited about, wow, chaos, what are strange attractors? What's it all about? So he wanted to see the infinite complex of surfaces in the attractor mentioned by Lorenz in his 1963 paper. In fact, I have Hénon's paper. I think it's in the abstract. Yeah, there it is. Lorenz has investigated a system of 3 first-order differential equations whose solutions tend toward a strange attractor. He is motivated to see what's going on in the strange attractor, so he comes up with a map. So rather than doing the actual Poincare map for the Lorenz attractor, which seemed numerically intractable because of this huge shrinkage factor, he set up a map where he could tune the shrinkage factor to the point that you could resolve things and see them. He came up with a simple 2D map with a strange attractor. And this was specifically devised to illustrate the fractal microstructure of strange attractors. It was the first direct visualization of this structure. Now, Hénon was a mathematical astronomer, and there are other things connected to his name, like the Hénon-Hales potential, which has something to do with the gravitational interaction of galaxies. This is not related to that. This is not related to physics. This was just a map he came up with mathematical properties to get at the structure he wanted. And he wanted it to be as simple as possible. So here's the map. It's 2-dimensional, so there's going to be an x and a y. So we can write it this way. xn plus 1 equals yn plus 1 minus axn squared. And yn plus 1 equals bxn, where A and B are adjustable parameters. And we'll see how Hénon picked the parameters that he wanted. But we could also think about how he arrived at this particular form of a map. It was obtained by thinking about, in some sense, stretching, folding, and reinjection. And notice it's just got one quadratic nonlinearity. That's it. But that's enough. Now, being a 2D map, it's different from the 1D maps, right? This is going to be something like, if we have x and y, it's our phase space, but if we start with some initial point somewhere, then the next point will just pop up somewhere else, and then pop up somewhere else, and then pop up somewhere else. and who knows what it may do. That's the orbit of a map in 2D. So we'll talk about how he arrived at this, and then some analysis of the map itself and what it leads to. We'll talk about its properties, and then something about the strange attractor that does result. So this is how he obtained this. He reasoned that he wanted, like we said, stretching and folding, and then reinjection. So here's the idea. So we'll think about it this way. This was a composition of several maps that each have a particular function. The first one was folding. We take an initial, in this case, let's think of a rectangle in X and Y. And I want to color things. So I'm going to color the left side kind of red and the right side kind of blue. And then maybe I'll make the top orange, bottom black. Then under a map that we'll call it T prime. This takes that shape and it will fold it into a boomerang. So we'll have, let me put the sides like that. Whoa. Whoa. We'll write these new coordinates as X prime, Y prime. They're not derivatives, they're just different coordinates. So you get this by, so the map T prime, so X prime equals X, so X doesn't change. Y prime equals 1 plus Y minus AX squared. So A here controls the amount of bending. If we were to put parallel lines in here, constant X, well, they would stay lines of constant X. Okay. Now the next thing we do, the next step is to squash. So it's kind of like stretching, but negative stretching, shrinking. We squash along the x-axis. So the next step is to squash. We'll call that T double prime. And this will just look like X double prime equals B. X prime, where we want the magnitude of B to be less than 1. So we're squishing. And Y double prime just equals Y prime. So these are both primes. So if you do that, then what do we get? We just squish this thing inward. So all you do a factor of B of, I don't know, something close to a half. So the Y coordinate doesn't change, just X. And you'll understand later, why am I fussing about making these colors what they are? It's just so that we can track things. So those green lines are now closer together by that factor of B. So B controls, think of it as dissipation, and by squeezing in, it does do some additional bending. So by dissipation, I mean shrinkage of phase space volume. In this case, volume it's 2D, so area. So now we've got this boomerang shape, kind of thinking of it as what we were saying before, as it's kind of like the folding and the stretching are happening in this first two steps. And then we are reinjection. He didn't call it that, but we can. So T triple prime would be the reinjection step. But we reinject, and we do it in such a way that we switch X and Y so that this boomerang shape is elongated along the X-axis, like the original rectangle. So we switch X and Y. I don't even know if he called it a boomerang shape, but it looks like a boomerang. So this is the original rectangle. So how do we do that? Just switching X and Y means we've got X triple prime equals Y double prime, Y triple prime equals X double prime. So it's like flipping, rotating and flipping. And what do we get? Really need to be careful about the colors here. So if we do this, we get something like this now. And if I were to track what those green lines were doing. So this is what the map does. And if you take the composition of these three, you get the map that we wrote up above. Let xn equals x, yn equals y, x triple prime is xn plus 1, y triple prime is yn plus 1, then the Hénon map, which we'll call T, is a composition of these three. So T equals T, we go from the order of operations is first T prime acts, then T double prime, and then T triple prime. And that gives us our final map. So that yields what we have. So T of xn, yn, that is xn plus 1, yn plus 1. Okay, so this stretching and folding accomplished pretty elegantly. Now there's some interesting properties to this. And Hénon was, again, motivated by the Lorenz system. The Lorenz system is an ODE, which means that every point has a unique back trajectory. And how we're talking about properties of the Hénon map. So like that property for the Lorenz system, that there is uniqueness, the map is invertible, which means that given xn plus 1, yn plus 1, there is a unique xn, yn, which we might write that as T inverse. And I want to distinguish this from what we did with 1D maps. With 1D maps, we did not look at invertible maps. So this is unlike the logistic map, right? For the logistic map, we could easily just graphically represent what was going on with some curve. So if we were at this point, we don't know where we came from, whether we came from this point or this point. So this was not invertible. There's not a unique inverse. The Hénon map does have a unique inverse. We could even calculate it if we so chose. So based on what the map is, xn plus 1 equals, it's just so easy to write down. The best things sometimes are really simple. Well, the first things that are studied are sometimes really simple. And this would be xn. Okay, so from this, we can immediately write, we could say, well, xn equals yn plus 1 divided by b. So, okay, that's the first one. How do we get yn? Plug this into the first equation. What do we get? Xn plus 1 equals yn plus 1 minus a. We've got that thing squared, so let's pull out a b squared, yn plus 1 squared. And just rewrite this to solve for yn. Equals xn plus 1 minus 1 plus a over b squared, yn plus 1 squared. That's the inverse map. So it's invertible, just like Lorenz ODEs. I mean, invertible in theory. Numerically, if you try to backtrack for the Lorenz system to try to find out, oh, where did this come from? I think once you're on the attractor, it's pretty hard. Information gets lost because round off error of things like Runge-Kutta algorithms. But theoretically, yes, through each point, there's a unique trajectory. And so you could do a back trajectory to find out what it is. The whole thing about practically, it's not possible. It's sort of separate. Here, it's theoretically possible, and we could theoretically get the inverse for the Hénon map as well, right? In the logistic map, it's not even theoretically possible to get an inverse. It just isn't happening. So we don't try. It has a unique inverse. It's invertible. It contracts areas, which should be analogous to how Lorenz contracts volumes. And how can we see this? Well, if you've taken calculus and you do a transformation of variables, a transformation of variables is like a map. The volumes, infinitesimal volumes, shrink or expand according to the Jacobian of your map. So you could just calculate the Jacobian. We'll write xn plus 1 equals f xn yn, and yn plus 1 equals g xn yn. We can calculate the Jacobian matrix. So the Jacobian matrix, write it as J. We write partial f, partial xn, partial f, partial yn, partial g, partial xn, partial g, partial yn. What do we get? Well, from the map, we've got it up above here. First entry, this is -2a xn. and this partial derivative is 1. Then for yn plus 1 equals bxn, so this is going to be b here, and then 0, because there's no dependence. So that's our matrix. The determinant of our matrix is negative b. And the magnitude of the determinant of the matrix is magnitude of b. So if the determinant is less than 1, then the map is area contracting. So this map is area contracting if b is between -1 and 1. And in fact, it's constant everywhere. If you remember from the discussion of the Lorenz equations properties and volume contraction, the volume contraction rate was the same everywhere, which until you've looked at a bunch of 3D ODEs, you don't know how rare that is. Usually volume contraction will depend on X and Y, places where you are in phase space, and it's not going to be uniform. But again, to try to follow and mimic the Lorenz equations, Hénon built in that the area contraction is the same everywhere. So using b between -1 and 1, we get area contraction. And in fact, it's the same everywhere, again, like Lorenz. I wonder if they met. I bet they did. That would have been a fun conversation. Okay, so areas are shrinking. Right? Areas shrink, which, okay, you can see how maybe that's a desirable property. Things will have to shrink down to something. Maybe it'll go down to a point, or whatever the analogy of limit cycles is in 2D maps, right? 2D maps are strange. They don't necessarily come from ODEs, so you can't think of continuous movement. They're odd beasts. Okay, so we've got area contraction. Good. What else? A bit like the Poincare-Bendixson, but significantly different. And again, a bit like the Lorenz system, but significantly different. The Hénon map has a trapping region that contains the attractor. It's not like Lorenz or, again, Poincare-Bendixson, where if you come up with some large region and the vector field is always pointing inward, right? There's continuous movement. And once you cross that surface, then you're just sort of stuck inside. You can't have that with maps because there's no vector field. There's just the mapping. So not all trajectories, orbits fall into the trap. So this is, in some sense, unlike Lorenz. Remember, for the parameter values for Lorenz, we said you take a large enough surface and everything was pointing inward. And that was part of the deduction of the Lorenz attractors. Well, things come in, they have to settle onto something in a bounded region. They're not going off to infinity in the Lorenz system. So they were either going to a fixed point or a limit cycle or whatever's left, some other alternative, which ended up being the case, some weird two-dimensional-ish thing. For the Hénon map, some trajectories escape to infinity. They don't just stick around the origin. And you could probably see that with the form of the map. Remember, it has that xn squared term, which means if xn is greater than 1, like much greater than 1, then the new xn will be much further away from the origin. So that's kind of the effect. So it's due to that xn squared term. We also wouldn't have nonlinearity without that xn squared term. So Hénon made some choices. We can even go to his paper. Tell us what's up, Hénon. So there's his map. He puts it right there. And he says numerical experiments are carried out for A equals 1.4, B equals 0.3. How did he choose those? Well, he needed the magnitude of B to be less than 1. And I think 0.3 led to pretty pictures, as did A equals 1.4. I don't know. Other than that, just as a note, Hénon chose parameters. So they're called the classic parameters, 1.4 and B equals 0.3. Just like the Lorenz system has its classic values. So the trapping region, and I'll be sketching what this looks like for the system. Down here, I'll just do between 1.5 and -1.5 for X, -0.6 and 0.6 for Y. There's this region. This is just a straight line from A to D. And then over here, there's a B and C. How did I do this? There's a straight line. And then we'll just make this one. So A, B, C, and D. It's a quadrilateral. These are the boundaries of the region. So the inside well, we'll call this region R. And if you look at where these all map to, it is rough to try to get this, but we'll call this like A prime, and this is D prime. The way this map was created was take a rectangle, fold, and all that stuff. So this is now C prime, and this is B prime up here. So we got those 4 points, and then it's just a matter of how are the other things connected. A through B, I think this goes to here, and then C to D. This, it kind of gets stretched like that. The bigger rectangle is R, and then where everything maps to inside, we would call this, right, T of R. And so how is this a trapping region? T of R is a subset of R. So if you start in R, here's some random point, then I'll end up here, T of P. And now continue this, T of P is also inside the trapping region, and it's going to map to something else inside this bent boomerang. And this is a sketch of what the trapping region looks like for that case. Now, how did we choose B? If you choose B to be close to 0, then you get very strong folding and squishing, but the sheets of the attractor will be too hard to resolve. And the whole point of this was to be able to resolve them. So you don't want like B to be 1/1000. You want it to be something. You don't want B to be close to 1, because then the folding might not be strong enough to produce chaos. Plus you won't get as much dissipation. So these were chosen because they worked and led to pretty things. So let me show you some things related to this. Here is a video made by the Professor Grist channel, which is really, really cool. On YouTube, you should check it out. But he's sketching that trapping region and then showing, I think, what it maps to, and probably in a better way than I was. I think this is like numerically accurate for the parameter values. And then we'll show a point. Here's an initial point and what its iterates are. Remember, they all have to, no matter where you start in the rhombus, the blue rhombus, you have to, all the future iterates must be inside the yellow boomerang. And as you move that point, well, once you move outside, some things might go off to infinity. So we could show that again. All right, that's what it maps to. Here's an initial condition, and its future iterates just color different weird colors. But right, if you take a point outside, take that point outside, its iterates will be outside, and this thing might escape to infinity. So unlike the Lorenz system, things aren't going to like fall through the trapping region and then stay in there. And the trapping region, right, if we chose different squares or different rhombuses, we might not find the trapping region. So it's left as an exercise to find the trapping region. This is just showing, for those classic parameters, here's an initial point and what it does, kind of near the origin. You see things are sort of staying within that boomerang shape, but maybe there's some interesting structure going on there. And here it is, just slightly varying that initial point. It still seems to be kind of seething along that attractor region. Oh, but then you go outside the trapping region and it goes away. Let me show you something else. It's taking a set of initial points on a grid and then doing the steps in that decomposition. So it's folding, stretching, re-injecting. Again and again, a set of initial conditions that started out kind of in a box centered around the origin. And you could see what's happening, right? It looks like we're converging onto something. All these initial conditions are converging onto a weird shape. And that is the Hénon attractor. So here's another view of the Hénon attractor. And you can see, so this has probably been resolved many, many times. If you were to zoom in, now you see even finer scale structure. So I would say Hénon achieved what he wanted. You can see this infinite complex of surfaces numerically. And if we kept zooming in, we would see more and more. In fact, he had that highlighted in his paper. The paper isn't very long. There's his steps. Here's the map. Let's do some numerics. And that's the attractor. That's what things seems to converge to. And then he zoomed in on a box somewhere. So he said, let's take that little box and blow it up. And then we get to this. So it's an enlargement of that region. And now he's saying, okay, zoom in on this box. It looks like there's, big, in that little box, there's a thick band and then two other bands. If we zoom in, what do we actually see? Well, what looked like a thick band is actually a thick band with two other little bands ad infinitum. You could just keep doing this. And because it's a map, it's actually much quicker than solving an ODE. There's this applet, and it simulates the Hénon system. So this is starting with an initial condition. It's actually a circle of initial conditions. So here's the first iterate of that circle. Press iterate again, and you kind of see how this seems to be randomly hopping around. Remember, it was a circle. And after just a few iterates, it seems to be converging onto this. They've actually flipped the sign of something here. So it looks like a mirror image of what I showed before, but it's going onto the strange attractor. For this website, there's also a button called randomize, which it creates like a cloud of initial conditions, for whatever reason, grouped near the origin. Maybe so you could see how the density of points move. And if you iterate this cloud, well, you see what happens. It's going quickly to that boomerang region. And I guess you could think of it as that boomerang region then maps into a boomerang within the boomerang, which then goes to a boomerang within the boomerang within the boomerang within the boomerang. So we can see the infinite complex of surfaces, and it's pretty cool. So he achieved what he wanted. Now there's lots of details about this. People have studied the Hénon map. There's a saddle point, a map version of a saddle point. So a stable and an unstable direction. The attractor is definitely related to the unstable manifold of that saddle point. Don't be deterred by the term unstable. Things that are unstable. So if I have like a unstable and a stable direction, and then I say, okay, this is a point, Q, and this is the unstable, let's say, positive branch of Q, and here's the unstable negative. These names come from the fate for things that are near the fixed point. So we say, oh, well, it's unstable with respect to the fixed point. But in terms of long-term dynamics where things will show up, they will tend to collect along unstable manifolds. They're like attractors. We call them sometimes attracting sets because things will tend to accumulate along the unstable directions of fixed points or other objects. The Hénon attractor is related to the unstable manifold of a saddle point of the map, a saddle type fixed point of the map. Now, if you do study more about 2D maps, it can be very confusing to try to interpret this because we want to think in terms of continuous flow, but there isn't continuous flow. So if I started, say, at this point on the positive branch of the unstable manifold, I will jump to some other point along it. And then maybe the next jump is really far away. And then the next jump, who knows, super far away. After this is done, who knows how many wiggles or something. And at first, this really confused me. So just letting you know. Whenever you see some kind of paper or something, know if it's a map or a flow. Because if it's a flow, it's easier. It's more intuitive. Maps, even 2D maps, are less intuitive, significantly less intuitive. I wanted to mention an experiment where you could see a strange attractor.